Josep and I are both electrical engineers. The good news is you don't have to be electrical engineers to understand our presentation. The second and third year students might recognise one or two of the slides. The other good news is that we're coming late in the morning with our presentation. A number of the speakers have actually covered some of our material. So we're going to be skipping through some of the slides quite quickly, so we might actually finish ahead of schedule. So I'm going to start off by going through some of the benefits for networks that energy storage can offer. When I get this going. Okay. So, a lot of you will know this, but in the UK, we have the transmission network, which is at 275 and 400 kV. National Grid own the transmission network in England and Wales. Scottish Power and Scottish and Southern own the transmission network in Scotland. National Grid have a role as the transmission system operator responsible for balancing generation and demand in real time. The distribution system has 7 different distribution network operators, and they cover from 132 kV down to low voltage, unless you're in Scotland where 132 kV happens to be transmission. So, going back into history, when the power system in the UK was originally designed, it was designed based on centralised large power stations connected to the transmission system, and you had power flowing down from the transmission system through the distribution network to your consumers. The transmission network was the only part of the network that needed to be active in the sense of trying to balance generation and demand. The distribution networks were relatively passive. You didn't need a lot of control and automation down at the distribution level. And in terms of designing distribution networks, it was very much a fit and forget approach to it. However, in the meantime, since the 1960s, when a lot of this was built, there's been a number of drivers for change on the networks. These have included performance targets set by the regulator. So, for example, things like customer interruptions, customer minutes lost, targets for reducing those. You've also got aging assets. The assets that were put in the 1960s are getting to the end of their life or past their end of their life, need replacing. You've got new technology, which we've talked about. Speakers have talked about the electric vehicles. You've now got greater scope for automation and control down at the distribution level in terms of the technologies that are available. Distributed generation, in response to renewables targets, we're seeing a lot more smaller scale generation connected to the distribution network. So what does that mean for the network? Fundamentally, there's been some very significant changes over the last 10 or 15 years. So you're now seeing at the transmission level, you're seeing some large offshore wind farms. You're seeing gas, combined cycle gas turbine power plants. You're seeing wind farms connected to the distribution network at all voltage levels. And you're seeing a lot more domestic level generation, particularly photovoltaic, which has had a significant impact over a very short period of time. You're seeing greater move towards electrification of transport in terms of electric vehicles, and you're seeing potentially quite an increase in demand over the next 10 or 20 years. So that gives a number of technical challenges for our networks and for us electrical engineers. There is a need for increased capacity on the network. We're seeing a growth in demand, as I've mentioned, but we're also seeing seasonal variations in demand changing. So you're seeing a lot more air conditioning in the summer months, and in some parts of the UK, you're actually seeing your peak demand in the summer, not in the winter, which is quite a change as far as the network operators are concerned. There's also increasing uncertainty as far as a network planner is concerned. They have to respond to connection requests from generation and demand. They never know how many of those are actually going to go forward into a real project, but they have to plan for it. So there's quite a bit of uncertainty as far as they're concerned in what they're doing with the network. There's increased difficulty getting new overhead line routes, so they need to make better use of the capacity that they've got. There's a greater need to balance the system, and Jill talked about this, about the issues with system inertia and frequency, and the system becoming much more volatile, and National Grid as the system operator having to respond much more quickly. Just on the left-hand side of the slide, I've mentioned another of the network innovation projects. Jill mentioned Leighton Buzzard. There was another one done for Northern Power Grid, customer-led network revolution, which include looking at a number of solutions to network issues, but also part of that was looking at lithium-ion battery energy storage. There is a very useful web link if you're interested in anything to do with network innovation, including the energy storage projects. This website has been set up by the Energy Networks Association, and it's got about 700 different network innovation projects on there now. So it's a good resource and it's searchable. So good place to look if you want more information. So coming back to how energy storage can help solve some of those problems, and looking at the distribution network operator to start with, Jill mentioned Leighton Buzzard and how that energy storage was used to solve some of the network capacity problems. We've done a piece of work which we completed this year for the Energy Networks Association called Distribution System 2030. And what we were looking at different types of distribution networks. So we modelled an urban network, a rural network, an interconnected network that looked rather like the ManWeb system, and an interconnected network that looked rather like the London system, because London and ManWeb are different to the rest of the UK in terms of how their distribution network is designed and operated. We looked at those networks over a period out to 2030 for different scenarios, and we actually did half an hour at a time throughout the course of a whole year looking at demand and generation and what the problems were that arose on the 4 different types of distribution network over that period. And then we looked at what solutions you could use to solve those problems. And amongst a number of solutions that we looked at energy storage. And there were some interesting conclusions that came out of that in terms of how useful would that energy storage be to delay investing and reinforcing your network. And typically it would be only for maybe 10 or 20 days of the year that you would have a problem where the peak demand on your network exceeded the capacity of the network and where your energy storage would be useful. And then typically, depending on the network, the number of years that the energy storage would put off actually reinforcing your network was maybe 4 or 5 years. It wasn't a long period of time, but there was benefit for the distribution network operator because it postponed a fairly major investment decision for them. So again, that report, if you want to go and have a look at that, it's the same network, same website link that I gave you on the previous slide. So the example that I'm giving here is showing how energy storage can solve a number of problems. So peak demand reduction, deferral of infrastructure investment, and just delaying that uncertainty. At the bottom of this slide, I've given another link, which is to a paper that we published in July. We did have some hard copies, but they've all flown off the table. So there's an electronic version of that if you're interested. And that gives a number of examples of how energy storage can be used to solve not just network problems, but a number of other issues for different types of owners. And this DNO case is just one of the examples that's in there. So if you're interested in the practical application and some of the costs and benefits, this gives a bit of a snapshot. We've talked about system frequency. Well, Jill talked about system frequency. This just tries to explain it a little bit more simply and talks about system frequency being a bit like a seesaw where you've got your demand for megawatts on one end and the megawatts supplied by your generators on the other end. If you have any increase in demand or you lose some of your generation, the system frequency reduces. If your demand reduces or your generation increases, then your system frequency goes up. And that seesaw wobbles a lot more when you've got a low inertia system. So that's just trying to explain it in a way that's a little bit clearer in terms of why frequency relates so closely to generation and demand. And this is a picture taken from, I think, it's National Grid's website, which just shows the sort of response services that they then need to buy to be able to manage that frequency in real time. And it shows the sort of time scales that are used when you're talking about frequency response services, ranging from a primary response where they want that additional megawatts available within 10 seconds, lasts for 30 seconds, through to secondary response, and then they also have reserve generation that they can bring onto the system in a longer time scale. Enhanced frequency response is what comes in the shorter time scale, and at this point I'm going to hand over to Josep, who's going to talk about enhanced frequency response services.
National Grid decided that to be able to manage the frequency efficiently, given that reduction of inertia that Jean mentioned before, they would open a new service called the Enhanced Frequency Response, which basically tries to manage that frequency on the short term. As we said, the facilities or the providers will need to provide a full output of the capacity in less than 1 second. We'll see that that the frequency deviation. Sorry, I was talking about another thing. The response of this capacity needs to be proportional to the frequency deviation, and they need to operate within an envelope that has been defined by National Grid, and that includes specific run rates within that envelope. The operators will have a deadband where they can manage the state of charge, for example, and during the hours that the providers are contracted to offer the EFR service, they cannot offer any other additional service. As we can see here, the minimum sustained delivery has to be 15 minutes and is quite high availability service. And we will see that this is one of the things that the providers need to consider, but we need to look at the practicalities as well, the whole project process. So the providers need to meet the technical requirements for National Grid, but they also need to look at what they want and the technical performance requirements. We look at lifetime, frequency of operation, efficiency, and we look at the size of installation and the different testing requirements. But all this is linked to, for example, the location of where this asset is going to be located. We're looking at different providers will have existing sites where they can locate these installations, or they look at new sites. They're going to go for containerized units and modular units where they can move across the different sites they've got for different purposes. Or they look at purpose-built buildings, and that has later an influence on the cost and timescales. But of course, they have to look at the environmental impact, all the issues like flood risk, accessibility, and of course, access to the grid. And in particular, we've worked with various clients on different projects, and the health and safety issue is one of the primordial issues they want to look at. They want to make sure that everything is down to standards. They want to, and if we look at lithium-ion, the phenomenal thermal runaway that most of you would be aware, is one of the major issues they are trying to sort out. They really ask about it, and they want assurance that this is not going to happen. There are other issues, of course, with regards to planning permission and whether these facilities want to be operated remotely. Other logistics like security and things like this, because obviously these assets will be protected. And then you have to look at the maintenance and how much, what's the cost, how many times you have to go on site to sort of fix an issue, and so on. And this has ultimately, obviously, everything is linked to the cost, and the cost is where the tender was evaluated on. So if we look at the EFR tender from National Grid, this is some early figures. We can see that there's been a huge interest from from battery storage to provide this service is 2/3 of the total capacity that's been pre-qualified. And when we look at the results that were published recently, 8 tenders were accepted. And some of these projects are quite big in comparison to what's been installed currently in the UK. And I mean, we talked about the 10 megawatt in Kilroot and the 6 megawatt in Leighton Buzzard. So, you know, we expect these projects to be a steep learning curve because there's going to be a lot more learning and technical challenges we expect. There's few technical details available about the 8 tenders that have been accepted, about the technologies they use. But, you know, looking at the market and how it is moving, it wouldn't be surprising that most of a large portion of them are batteries and perhaps lithium-ion. We also, you know, can say from these results that the winners have been predominantly renewable EPCs and developers, which to us it means that, you know, there's the link between the renewable industry and the battery industry is strengthening. So all these results and all the tenders submitted tells us that the battery providers, the battery manufacturers, are quite confident that they can provide this service. The answer to the question on can lithium-ion be or meet system requirements, well, I think it needs to be seen because, you know, once we have more data available on how these projects perform, we'll be able to really determine. But, you know, it looks promising because, you know, lithium-ion has the capability to respond quickly. It's high availabilities. It's also high capacity. But we know that National Grid is planning to open another tender in a few years, probably twice the size. But I suspect they want to wait and see what the results of these first projects are first. And that's pretty much for me, I think. I'm going to skip to the last slide because I think that has been covered. Thank you.